Good evening and welcome. My name's Ted Kesik. I'm a professor here in the Daniels faculty, and one of the fun things I get to do is coordinate this lecture series. It's always been a thrill, and I can't believe it. We're in our 6th year. I don't know where the time goes. It flies. They always say time flies when you're having fun, and we've certainly had a lot of fun in this room over the past 6 years, and it's going to get better tonight. Most of you know that if you're a practicing architect and you're looking to get some continuing education points, that there's forms that you can fill out and you leave them and then we process them. Some people were here in a previous lecture earlier on this semester, and those certificates are being processed, but we thought it would be more in the keeping with the festive spirit of Christmas if we sent them out, in December. It would feel better if you got your certificate. It'd be like a early Christmas present, right? So that's the reason. The real reason is the students that process the certificates are busy. This is that time of the year. It's a crazy time of the year. And those of you who've been through architecture school know what I'm talking about. I'm talking about those last few weeks before year-end reviews and thesis and all that wonderful stuff. So anyway, that's just to explain that part of it. I'm always grateful to Tremco Roofing and Maintenance because they've been our steady sponsor, and it's been a great relationship working with them and making sure that we could always put this lecture series on every year. So before I introduce this evening's speaker, I'd like to invite Sean McCallum of Tremco Roofing and Maintenance just to personally welcome you here tonight. Sean?
Thanks very much, Ted. As Ted alluded to, my name is Sean McCallum. I'm the Ontario Regional Manager for Tremco Roofing and Building Maintenance, and it is my pleasure to sponsor this event on behalf of my company, and it's been a real pleasure being involved for the past 6 years. I've attended many of these lectures, and they are all fascinating. Even though not all of them have anything to do with roofing, it's a real pleasure to be associated with it. So for those of you who don't know Tremco Roofing and Building Maintenance, we are a local manufacturer here of high-performance building systems and solutions. We've been on the same street corner in Leaside for the past 85 years. We run a zero landfill facility there. We'd love to take anyone on a tour if any of you are ever interested. The vast majority of our business in the Ontario market anyway is driven through third-party architects, engineers, design professionals like yourselves. So I wanted to thank you for that. For those of you who do specify Tremco, not everybody cares about roofing as much as we do. Sadly, all the guys who work for me are, they live and die and breathe roofing. So I know most of you may not care as much as we do. So if you ever have any questions or if there's anything you feel like we can help you out with, I hope that you would reach out to me and we'd be happy to help you out with whatever we can. So once again, thank you for your business, and we look forward to this evening's event. Thank you.
The first time I met Ryan Danks was at a ESIM conference in Ottawa this spring in May, and it's a conference for ESIM stands for electronic simulation or energy simulation. No one can remember because the conference has started so long ago. There's arguments over what ESIM stands for, but we all know what it is. And it's run by the Canadian chapter of the International Building Performance Simulation Association, which is known as IBIPSA Canada. So, we had a bunch of interesting papers that were presented, and among the most interesting, of course, to everyone there was what Ryan presented. And I approached him and said, "Would you like to come and be a speaker?" And he said, "Well, I'm a U of T alumnus." He said, "I'd be happy to come." He said, and I said, "Well, great." So. For those of you who don't know anything about Ryan, he's an engineering science graduate here from the University of Toronto, and now he's with RWDI Habitat, and basically he works mostly on research and development of tools and methodologies to better simulate the interaction between the built and natural environment. So his plate is full because everybody wants answers to questions that are tough, and I think he's the guy that if anybody's going to crack it, he'll do it. I know the end size. You guys are always brilliant in engineering, and I know you'll do it. It's just, we're just worried about how much beer it's going to cost us to get the answer, really, in engineering circles. But maybe not that much. Who knows? We'll find out tonight, later on, when we're relaxing after the talk. So it's my pleasure right now to introduce Ryan Danks, and I'm really looking forward to your presentation. Thanks for coming.
There we go. Well, thanks for that introduction, Ted. That was too kind. I am Ryan Danks. I'm an engineer with our WDI, but hopefully you won't hold that against me. My goal with tonight's lecture is to get you all thinking a little bit more about the ways that our built environment, the things that we build and design, interact with the sun, and maybe in the future change how we do that to better take advantage of the sun, minimize its negative impacts, and maximize the positive impacts. So what do I mean when I'm talking about solar impacts? Well, there's lots of things. Glare, there's shadowing, daylighting, thermal comfort. All these things are interactions that happen between the sun and the things we build. And they mainly depend on those three parameters. Where you're building, which dictates where the sun is in the sky, what your building looks like, which defines things like how much facade is exposed to sun, and then the facade itself, which defines how much light's transmitted into your building and how much is reflected away. Now, the challenge in working with the sun is that changing any of those three parameters has knockoff effects on all of these other characteristics. So if you optimize your building for daylight, you could run into issues with glare or thermal comfort. So the challenge is really fine-tuning in design each of those, anything you can really in terms of the building layout to really try to find the best balance for all these different impacts. I actually had a lot of problems trying to come up with this slide to show it because these things are so interconnected, it just ended up being just this rat's nest of lines over the whole thing. So I figured it might be a little bit easier to go through these step by step. So we'll start at the source. Here's the sun, in case you weren't sure what I was talking about. It's the single biggest source of energy on Earth. In just an hour and a half, the Earth receives enough energy to power all of human civilization for a year. But despite this tremendous amount of energy being imparted onto our buildings, we really don't pay too much attention to it in design, which is kind of weird because we used to. Traditionally, the sun was our main source of light and heat, and we developed as a civilization a lot of different ways to handle that. So the image in the top right here is called a masharabiyah. This is an ancient Middle Eastern technique. There's examples of these going back to at least the 10th century. And what it is this carved screen that gets inset into a window. And what it does is, in addition to providing privacy for people living there, it breaks up those direct sun rays into the building to minimize heat gain while still allowing enough light through to light the space. The porous nature of it also helps to maintain some airflow to keep the rooms cool. A more recent example is in the photo on the left there. That's New York's Flatiron Building circa about 1912. Now, what's interesting about this picture is that almost every single window with an eastern exposure has an awning. At this point in time, the windows were actually designed to incorporate this feature that people would be putting on awnings in the summer and taking them off in the winter, because it was really the only way to minimize those solar heat gains during the day. And I can't even imagine somebody trying to sell this on a modern building. This same sort of technique carried all the way through the 20th century. It shows up even in residential construction, like the very large overhangs you see in the prairie-style home here in the bottom right. But as time marched on and we used more electric lighting and we relied more and more on HVAC, we really kind of forgot and started ignoring all these effects. It was easier to just add lights or turn down the thermostat. But we're at a point now where we really do need to start considering the sun again. And there's a few good reasons for that. The first is that our cities have become denser. We've got more people and more buildings in ever-shrinking areas. That means the odds of some sort of negative impact occurring have gone up, and the number of people potentially affected by it goes up as well. This increased density has also forced us to build buildings taller, which has obvious implications from a shadowing perspective. We also use more glass than ever before in our designs, which, while good from a daylighting perspective, poses some real challenges in terms of heating and cooling and glare. And finally, modern building design and technology has kind of freed us from building only those prototypical box skyscrapers. We're now only really limited by our imaginations and, of course, budgets. But what the consequence of that is that the old rules of thumb and experience-based knowledge for these square buildings don't necessarily apply, or apply in different ways when the building is a more organic or curved shape. So hopefully I've convinced you that this is a good idea to think about these sorts of things by this point, but if not, maybe these next slides will. I'm now going to talk about what happens, or what can happen, when you don't think about the sun in design. So the first consequence of a poor interaction is, of course, publicity. I know there's no such thing as bad publicity, but I don't think anybody in this room wants to become well known for building death rays or blotting out the sun. I mean, unless your clients are supervillains, then maybe that's a good selling point. I don't know. But maybe you don't have much faith in the general public. They do tend to have a pretty short attention span. So maybe you could live with a couple weeks of bad press and then everyone forgets about it. But there's better reasons to think about how the sun impacts your buildings. And one of those reasons is the fact that cities and green building standards make you care about how your buildings interact with the sun. Cities all around the world, including right here in Toronto, mandate tall buildings to conduct a shadow study to make sure there's not an excessive amount of shadow created by your building. More recently, we're seeing cities try to regulate the reflectivity of facade elements to try to reduce the risk of glare. And of course, there's the green building standards, LEED out of the US, BREEAM out of the UK, GSAS and Estidama out of the Middle East. All of these standards reward buildings which have intelligently incorporated the sun into their designs. Now, that's primarily through rewarding good daylighting and heating. But in the Middle Eastern ones in particular, there's also points available for master plan developments that have good outdoor shading, because that's a key component of maintaining walkability through the very intense summers. But maybe you work in some sort of libertarian paradise where there's no rules, you can do whatever you want. There's still one last and maybe the most important reason why you need to care how your buildings interact with the sun. And that is that it is often very, very expensive to fix problems after they've occurred. I've got two examples here that hopefully illustrate this. The image on the left was taken at a small airport in New Hampshire. They installed an array of solar panels on the roof of a parking garage. And rather quickly, they realized that in the early morning hours, the sun would reflect off these panels directly into the air traffic control tower. Obviously, that was not a good thing, and they quickly had to run out there and cover about 25% of those panels while they could come up with a more permanent solution. Ultimately, what they ended up doing was rotating all the panels so the reflections would miss the tower. The problem there was that now that these panels weren't pointed south, they weren't generating as much power. So in addition to all that work, they had to build more panels to meet their energy production quota. The image on the right, you might be a little more familiar with. This is the 20 Fenchurch building in London in the UK. This is the one that made headlines last year for rather famously focusing enough sunlight at grade to damage a Jaguar sports car parked across the street. Again, they had to kind of quickly throw up scaffolding across the street to block these reflections while they could come up with something more permanent. In this case, they built essentially a 31-story brise soleil. If you're not familiar with that, that's kind of a modern take on a mashrabiyah. But the difference here is instead of breaking up the sunlight entering the building, this was designed to break up the reflections leaving the building. Both these cases represent millions and millions of dollars that didn't need to be spent. It's a point we try to hammer home to our clients all the time, is that it's really in your best interest to look at these sorts of issues early on, because it's a whole lot cheaper and easier to fix your building when it's ones and zeros than when it's bricks and mortar. So hopefully by now I've convinced you, without a shadow of a doubt, that this is a good thing to study. If not, the rest of this presentation is going to be kind of boring, because I'm now going to talk about some of the more important solar impacts in a bit more detail. The first thing I'm going to talk about is shadows. This is something that we're all pretty familiar with, I hope. But the challenge with working with a building that has a shadow problem is that you can't mitigate it. You can't uncast a shadow in a built building. Short of tearing it down, there's really nothing you can do. So that's why it's critically important that you understand how the shadows cast by your building will behave. And it should come as no surprise that this is the most common type of solar-related building regulation around the world. And so what do those regulations force you to do? Well, they usually have you create images that look like this. These are called shadow extent plots. I pulled these two from the City of Toronto's planning website. And so what you have to do is bring in a 3D model of your building into a piece of rendering software, position a light source where the sun would be for a given day of the year and time of day, and create an image showing where the shadow of your building is cast. Now, these are good, and they're helpful in their own way, but they can be cumbersome to use, and they don't necessarily tell the whole story. And I'll use a little example to hopefully illustrate my point. So here's pretty typical low-density neighborhood, about 65 acres. Everything's 2 or 3 stories. Now, unfortunately for this neighborhood, it has become very trendy. And as often happens in trendy neighborhoods, someone's planning to build a condo tower in it. The neighbors are understandably upset about this, and the city has ordered a shadow study to be conducted. Now, at the bare minimum, these shadow studies need to look at the shadows cast during the daytime hours on 3 key days of the year. The summer solstice, when the shadows are their shortest, the winter solstice, when the shadows are their longest, and one of the equinoxes when they're in between. So that way you've captured kind of the full range of shadows at your site. So let's take a look at what those look like for this building. So here's our summer solstice. Nothing really dramatic going on here. The buildings immediately to the east and west of our tower are taking the brunt of it, but the rest is kind of contained to the site and the street. Moving on to the autumn equinox, now things are getting a little bit worse. We're casting a much longer shadow. We've reached across the street, so now we're impacting those buildings to the north of us as well. And the winter equinox, this is the one that makes people sweat when they see this a lot of the time. We're casting a massive shadow here. We're multiple city blocks long, impacting dozens and dozens of houses. So why do I think that this method has some shortcomings? Well, it makes it difficult to understand a few key points. The first being that there's really no easy way to understand the frequency or duration of these shadows. It's great that you can say at 9:18 the shadow is going to be there, but how long is someone's backyard going to be shaded? You could maybe do that by flipping through multiple images or doing them at shorter time steps or for more days, but that just adds work, and in the end, it's still up to the reader to kind of figure out and make those estimations of how long. You're also not necessarily able to tell if a shadow would have been cast anyway. I made these using a piece of custom software, so we're able to cast the shadows in different colors depending on the source. But a lot of rendering software, you can't do this. So for this big guy up here, you would just be left with a big blob of black, and it would be, again, up to the user to try to figure out which areas would have been in shadow anyway and which is new shadow. And the biggest drawback in my mind is that these are really cumbersome reports, both to generate and to read. You end up with dozens and dozens of pictures all scattered through this report. So for those reasons, we try to take a different approach whenever we can. And that's to create plots that look like this. So what we do is at 5-minute increments over the course of an entire year, we determine how often, the percent of the time, each point on our at grade is in shadow. Now the 5-minute time step's kind of arbitrary, but once you get lower than that, you really don't see much of a difference on these plots. So we generate this information both under the existing case and with our new building, and then subtract them. So now we've distilled all that shadow information down to one plot. And in my mind, this is a much better approach to take when it comes to shading, because we've been able to remove the areas that were already in shadow. And remember those giant, scary winter shadows, now suddenly they don't look so bad. And it's not because we've done any voodoo to it, it's just because they're not very frequent, and a lot of the area that would have been shaded, that was being shaded by our building, was already shaded. Now, I'm not saying that this building is great from a shadow perspective. Obviously, there's still a huge area here that's being terribly influenced by this building. But at least now we're being fair to both the building and the neighbors. We're not unfairly penalizing a building just because it's tall. Another aspect that's often missing from these shadow studies that's really important, or can be really important, is the effects on the buildings themselves. These are results from a project we did in Russia, where part of their building code mandated that residential apartments needed to have, their windows needed to have, on average, at least 3 hours a day of sunlight exposure. Now, obviously, for southern exposures, that's pretty easy, but for the northern exposures and for some of the buildings on the interior of the site, that was actually a bit of a challenge. So we worked with the architects and the master planners to change orientations and positions to try to maximize the amount of facade area that hit that target. But building codes aside, this is something that really we don't care too much about a lot of the time. And that's because, but really we should, especially going forward as we integrate more sustainable features into our buildings. If we jump back to our unfortunate buildings to the north of our condo tower, if these were conventional homes, what we have here really is a nuisance more than anything else. But if one of these houses had rooftop PV, now suddenly you've impacted those people financially, which is something that's a lot more actionable in legal speak. The bigger problem would be if those houses were something like a passive house, where now you've significantly cut the amount of sunlight available to it, which has a direct impact on its ability to keep itself warm. So if these shadows are mainly occurring in the winter, you've potentially created a safety hazard for the people living in there, because now that the supplementary heat system may not be able to keep up because there's so little sunlight. To my knowledge, these sorts of problems are still very, very, very much few and far between. But like I said, as we integrate more sustainable features into our buildings, these types of problems will start to occur. Another knockoff effect of shadows is the fact that they impact the ability of plants to grow. Now, admittedly, this is maybe a bit more niche, and a lot of you may not really care, but it's still a very interesting application of this sort of work. Now, we mainly do this sort of work when people are designing stadia, but it applies just as well for any sort of high traffic area like a park or a golf course. And the reason it's important to particularly stadia owner is that having a high quality, consistent playing surface is really important for the safety of the players. A field that yields or doesn't yield to their movements in a predictable way could be the difference between scoring the winning goal or a career-ending injury. So imagine if every day when you went to work, the floor shifted between concrete to rubber to sponge. And that's the kind of things they could potentially be dealing with. Not very safe. So the club owners it's really in their best interest to make sure the field is at a high level because no one wants their $1 million player sitting on the bench. It says it up here on the slide, and I'll reiterate that. We didn't work on this stadium. I read about this in a trade magazine, and it's just a really good example of why you want to conduct these kinds of studies. So this is Gamla Ullevi Stadium in Gothenburg. If there's any Swedes in the audience, I apologize if that's wrong. It was built in 2009 to host 4 local teams as well as the Swedish national women's team. So this is a field that gets a lot of traffic, so making sure you get enough daylight to the grass so that it can heal itself after games is really important. In a nod to keeping the spectators comfortable, they built these very large shading canopies around the perimeter of the stadium. Now, unfortunately, in addition to shading the stands, they also shade a pretty significant portion of the turf. And as you can imagine, it's difficult enough to grow grass in Sweden all year. So all this extra shade really doesn't do them any good. What they ended up having to do was purchase these mobile grow light systems. And so what these are lighting rigs with lights that are specially tuned to mimic the specific wavelengths of light that plants use to grow, the PAR wavelengths. And so they wheel these guys out in the evenings after the games are done and use that to provide some supplemental daylight to the grass. Now, I'm not saying some clever design tweak could have eliminated this use. I don't know enough about the project, but a better design may have been able to at least reduce their use and save the team some energy. Here's a project we did work on. This is Center Court at Wimbledon. In 2006, it was undergoing renovations to add an extra 10 rows of seats and a retractable roof. So that way the matches could continue through intense heat or, because it's England, rain. The concern was that all this extra structure was going to reduce the amount of daylight the court gets and impact its quality. So for this one, what we did was first analyze the daylight levels under the existing stadium design. And then that became our benchmark as we went forward and tested various design alternatives proposed by the architects. And with a bit of back and forth, we were able to design a roof configuration that really very, very minimized the difference in daylight levels, particularly during the important summer months when the Wimbledon tournament is going on. So there's a nice positive story to contrast with the last one. We talked about buildings, talked about plants. Let's move to the top of the food chain now and talk about people, specifically keeping people comfortable. These thermal comfort studies are something that have been done for a while now, at least 10 years, but mainly in extreme climates like the Middle East or the far north. More and more now we're seeing them done in more temperate climates because there's a very obvious connection between how comfortable people are outside and how walkable that area is. It doesn't matter how walkable your neighborhood is on paper, how close you are to a grocery store. If it's terribly disgusting hot outside or freezing cold, it reduces the likelihood that people are going to walk. So the natural question is, how the heck do you decide if someone's comfortable or not? And it is kind of a finicky thing because you're talking about perceptions. But through many, many years of analytical models and human experimentation, we were able to, science was able to come up with some metrics for scoring comfort. And most of them depend on these 6 key parameters. 4 of them define your environment, so the temperature, the humidity, airspeed, and the solar levels, and 2 that define the person themselves, their activity level, how much heat your body's generating, and how well your clothes insulate you. With these 6 parameters, we can come up with a wide variety of metrics to define how comfortable something is. So how do we go about doing that? Wind and sun are the 2 most variable components of this. So those you have to simulate directly. In this case, this is Hamad International Airport in Doha, Airport City, I should say. So the first step was conducting computational fluid dynamics, CFD simulations of the predominant wind directions, and take a look at how the local built environment affects those wind flows. So advice at this stage would be something like, if there's a very clear shift between summer and winter winds, align your streets with those summer winds to promote good ventilation through your streets, and then block off those winter winds, which are going to be cold and uncomfortable. So we repeat this analysis for all the predominant wind directions on site. We then shift to the sun and look at kind of the frequency and the intensity of solar levels over the entire domain. And again, same sort of advice, mainly talking about massing and street alignments. East-west running streets are usually not very good. That's exactly where the sun travels. They provide minimal shade. Oblique angled streets usually do the best. In both these cases, the fidelity of your simulations are really, really important because it's thermal comfort is something that can change within a few feet. Just stepping out into a shadow, out from a shadow, can have a dramatic impact on your comfort. So you can see in this case, we were actually able to acknowledge the shadows from individual trees. And that's, unfortunately, the level of fidelity you need. So it makes these simulations kind of cumbersome. Once we have a good idea of the wind characteristics and the sun characteristics, we can then combine it with climate data and assumptions about what people are doing and wearing to come up with our comfort metrics. So this is a side-by-side image of kind of the central mosque area of this master plan. And the idea here was to show the effectiveness of the client's proposed landscaping plan. It's not really surprising that in the Middle East in the summer, the sun is the dominant factor in your thermal comfort. So being able to provide any shade at all is really important, whether it's done through trees or canopies or buildings. And so we were able to create really a very, very long continuous area along the buildings that had very good shading levels. We were taking areas that would have been intolerably hot into something that you could at least tolerate for a few minutes. And this has a direct impact on walkability within that site. This is another project we worked on in Qatar where we did something a little different. We mapped the thermal comfort results directly onto the walking routes identified by the master planners. And what we did with this was kind of create a day in the life narrative. You know, so-and-so leaves their house, they go to mosque, they get a coffee, they go to work, et cetera, et cetera, et cetera. And by analyzing the routes that they would take and combining that with the thermal comfort statistics, you could make a reasonable attempt at estimating how often they would make those trips by foot or choose to drive if it was too uncomfortable. And once you have those statistics, you can get a really good understanding of the true walkability of your site. You've gone beyond, you know, distance-based walk score kind of metrics and really incorporated the human factor, for lack of a better phrase, into those walkability metrics, which was kind of a neat usage of this technology. Move inside now and talk a bit about daylighting. I'm sure a lot of you are familiar with this. It's something that's become very, very popular in architecture. But for those who aren't familiar with it, daylighting is the art and science, and it really is an art, of finding the balance between light and heat inside of a building. You need to be able to provide enough daylight to a room for people to work in a comfortable way without overlighting it and without underlighting it and without creating too much heat. So it really is a very, very difficult balance to strike. These are images from another project in Saudi Arabia we worked on, the King Abdullah University of Science and Technology, or KAUST. The images on the left were actually part of a study we did to create a naturally ventilated and fully daylit parking garage. I like that project because it's a really nice example of taking even the most mundane structures and making them sustainable. This parking garage, if the sun's out and there's not a fire, you do not need any power to this building. It's fully naturally ventilated and fully daylit. The next example I'll talk about is something a little bit different in that we were part of a team for a design competition. We were part of OMA's team for the competition to design the new headquarters of the Axel Springer company in Berlin. The twin challenges on this project were the very short timeline and also the very, very aggressive daylighting target that the client had set. So the first thing we did is do what we call a daylighting assessment. So we looked at the illuminance levels on the facades of all the nearby buildings just to get an idea of, is it even bright enough in Berlin, in the middle of the city, to achieve these daylighting targets? Luckily for us, it was. So we were able to move on to the next part, which was optimizing the building itself. We did many, many rounds of studies, many, many iterations, looking at the glazing, looking at these light shelves here, their density and size, looking at the positions and sizes of skylights and light wells. And the reason we had to do so many iterations was because we had to strike that balance. We would come up with a solution that was great for daylighting, but then the mechanical engineers would come back and say, no, you can't do that. The HVAC system won't be able to keep up with the heat gains. So it was a lot of back and forth with all the different members of the design team. Ultimately, though, we did hit on a solution that everyone could agree on. And then we performed one last set of daylighting simulations, which was packaged up and submitted with OMA's bid. And OMA ended up winning, so we were all pretty happy about that one. The last impact I'm going to talk about, I'm going to spend a bit more time talking about this than the others. And that's because dealing with reflections and glare, there's a lot of nuance to what's going on, and some of it's kind of counterintuitive to people, and there's a lot of misconceptions. And it's also something that can actually be really dangerous. There have been many studies that have shown even a small amount of glare in a driver's line of sight can significantly impair their ability to drive. So when I talk about glare, this is probably what you're all picturing, an area of your field of view that is significantly brighter than the rest of your surroundings. It can come from the sun itself, it can come from reflections off glazed surfaces, like that image in the middle, it can come off metals, like this steel roof. Fun fact about these pictures, that's actually my desk at work. A couple months ago, the shade in the skylight broke, and every day at about 4 o'clock, I got this very, very intense beam of sunlight directly on the back of my head. The irony of that was not lost on my coworkers, I assure you. But it did provide a nice excuse to leave early. Now, I'm not going to talk so much about indoor glare, and that's because there are already several very good metrics that let us understand the impact this will have on people, daylight glare potential being one of them. It's also a little bit easier to fix, albeit in a brute force way, by closing blinds or by moving your desk. And it really doesn't pose too much of a danger to people because they're not forced to stare at it all day. But when we go outside, that becomes a different story. There really aren't any universally accepted metrics for saying how much glare is too much outside. The metrics we use inside and the metrics we use at night to assess glare from headlights or street lamps just don't work during the day. Things are just way too bright. And it's also, this glare is also significantly more dangerous. Like I said, glare coming from the wrong direction will really impact the ability of a driver, or worse, a pilot's ability to see and safely control their vehicle. So in absence of any universal metric, what we like to use is a scale developed by the very smart people at Sandia National Labs in the US. They do a lot of work on solar power and have created kind of a ranking scale for glare, which is a combination, based on a combination of the reflection's intensity and its size. So at the top of the scale, you've got glare that's bright enough to actually burn the back of your eyes. Thankfully, we don't see that one too much in our work. The middle range here is glare that's bright enough to cause after imaging on your eyes. So like when someone sets off a bright camera flash in a dark room, those blobs of color you see after that. And then the lowest range of glare are ones that really don't have a noticeable physical effect on a person. We make a slight modification to this scale because it's missing one key component, and that's this concept of taking into account the activity going on when someone's experiencing this glare. So we add an extra category. Low is still low in our scale, dangerous is still dangerous, no getting around that. But when we detect in our simulations glare that's too bright enough to cause those after images, that's when we have to look at where it's coming from and what the assumption is of what people are doing at that point. So if you're dealing with one of these after image level glares and you're in a cafe eating lunch, or you're walking down the sidewalk, or it's glaring at you while driving from the sides or the back, that's not necessarily a big deal. It's a nuisance for sure, but it doesn't necessarily put anybody at risk. You can kind of easily look away or deal with that temporarily, so we call that moderate. What puts you into the high category is if you've got these after images occurring from a glare source directly in the line of sight of a driver. Now you've caused a physical impact on somebody's eyes that's trying to drive 1,000 pounds of car at 60 kilometers an hour. So these are the kind of reflections that we really try to warn our clients about. The flip side to visible glare is thermal glare. And this is something that doesn't get as much thought, I find, because it's invisible. In addition to reflecting visible light, these surfaces, glass and metal, will also reflect thermal energy, infrared. The images on the left here were taken across the street from 20 Fenchurch during its Week of Fame last year. That's the wing mirror of the Jaguar that got damaged. You can see it's sort of softened and deformed the plastic. But what catches a lot of people off guard is you don't need to worry about it. In addition to worrying about this with giant buildings, this can happen at much smaller scales. These images here are of damage caused by regular residential windows. In this case, it was hot enough the reflections were hot enough to blister the paint, and in this one, it actually deformed the vinyl siding. Now, I talked about temperature there, and one word of caution if you are looking into issues with glare, it's kind of misleading to talk about temperatures because it's not just dependent on the intensity of the reflection. That isn't necessarily a one-to-one sort of relationship. Yes, the temperature will rise if the glare is more intense, but it also depends on a whole host of material properties, what the objects are connected to, and the wind speed more than anything. The difference in wind of just a couple of meters a second will cause a 10 to 20 degree change in your temperatures. So throughout the rest of this presentation, you won't see me talk about temperatures too much, and that's why. So we've established that glare can cause a lot of problems, but how does this happen? Well, there we go. Well, part of the problem is the properties of the glass itself. This is a schematic of a pretty typical double pane window. And when you spec glass, as most of you know, you will get a number indicating how reflective it is on the outside. In this case, the spec is 11%, meaning for every 100 watts of energy hitting the outside of that glass, 11 will be reflected back out. Now, the catch is that measurement or calculation was done for light rays that are hitting perpendicular to the glass, hitting it broadside. The problem with that is that it changes. Once you get past this critical angle of about 50 degrees, the reflectivity of the glass dramatically increases. And now this is just a fundamental property of glass. You can't get away from this. I won't get into the gory details, but this is a consequence of the physics of light moving through air and hitting glass. Anti-reflective coatings, frits, tints, none of those will change this. Even solar panels will experience this same phenomenon. It won't get quite so high because it's absorbing a lot of it, but you could still see a 5, 6, 7 times increase in the quoted reflectivity when you have light hitting at these glancing angles. And this is why those blanket restrictions on facade reflectivity aren't necessarily a great idea, because the reflectivity of the facade, even if you're below whatever the threshold is, depending on how the light hits your building, it's still going to be more reflective. So the only way those kind of blanket restrictions work is if everything on your building is matte black, which obviously isn't very practical. There's 2 lines on this graph, and often in specs for windows, you'll see 2 numbers. It'll talk about the visible light reflectance, so the fraction of light that we can see that gets reflected, and the fraction of the full solar spectrum, visible plus the thermal. Now, most of the time, those numbers are pretty interchangeable. They're pretty close when you're using typical glass. But look what happens when we go to a low E coating. Visible light stays the same, but our full spectrum reflectivity has tripled. And this is something that also catches a lot of people off guard. They think they've spec'd this really low reflectivity glass, but they're still having thermal-related reflection issues. And it's because it's got something like a low E coating, so you're reflecting a lot more of this thermal energy. And if it's happening at a glancing angle, it's even worse. And so why does this happen? Well, that's how low E windows work. The coating is designed to allow visible light through and reflect the thermal away. And so you have to be aware when you're speccing out the windows, if you're going to use a low E coating, that's fine. But you need to look at both the visible and the full spectrum reflectance in order to get a really good idea of how it's going to behave. In addition to the properties of the glass, there's also geometric concerns you need to think about when dealing with glare problems. Here's our double pane window again. This time we're looking at it in plan. What can happen with a lot of double pane windows is a pressure difference will develop between the outside of the window and the air gap in between. This causes the panes to deflect in. And what you end up with is a parabolic curved shape like this that is a very, very good focusing reflector. If we go back to our vinyl melting reflections, you can see in the image here that there's a lot of different looking reflections, and that's because of this curvature. This square reflection here is likely from a window that, for whatever reason, hasn't deflected. This round but dim reflection likely came from a window that has deflected, but this wall is far enough away that we're on the other side of its focal point. These ones here are the problems. You've got a very, very focused reflection, so we're likely this wall is right in that area. And this is where you run into problems because you've got a lot of energy being concentrated in a very small space. The same sort of thing will happen at larger scales, the building scale, if you've got a curved facade, a concave facade. And for these cases, it doesn't really matter if the individual panes have deflected because the whole building is acting like a reflector. If your facade is straight in the vertical, what you'll end up with is sort of a focal line. And this line will kind of move up and down as the sun changes in elevation and move side to side as the sun goes from east to west. If you've curved your building in the vertical as well as the horizontal, this is even worse now from a glare perspective because you've created a focal area. No matter where the sun ends up, the vast majority of the reflections from this facade are going to end up in the same area. And so these are the ones where we often see problems. So here's admittedly a pretty contrived example of what can happen. This is a curved facade with low E glass on it. So you can see in the plan view there, you've got your focal point that is a fairly consistent distance from the facade, and it tracks along the parking area there. And in the isometric view, as the sun gets lower in the sky, you can see the height of the focal area change. Now, the reason why I invented this building to show these problems is because it's nothing really dramatic. It's kind of a boring curved building. It's a building designed by an engineer. But the point is that it's really easy to accidentally create cases like this if you're not careful. And in fact, these sorts of focusing events are probably happening in a lot of buildings, but the focal points happen to be in midair, or they're happening in less populated areas like roofs or in parking lots, so we never really notice. So I've talked a lot about the problems. I'm sure you're all interested in what you can do to fix them, or maybe more importantly, how to prevent them in the first place. So the first thing you really need to think about is the orientation of your facade for the facades that are frequently exposed to daylight. So in the northern hemisphere, the sun stays mainly in the south, tracks east to west. So it's the east-west and especially southern-facing facades you really need to be interested in. And so here's sort of three prototypical facade types and their resulting reflection patterns for the sun being at the same point relative to the building. So here's a convex facade, a facade that curves out away from the building. It creates sort of this pinwheeling pattern here. The upside to this type of facade is that there's no way for focusing to occur because of the geometry. You'll never get a reflection that's brighter than the sun. And you'll also have reduced chances of thermal effects, because as these reflections kind of move over the course of a day, any given point will be subject to a quick little increase in irradiance, then it'll go back down to ambient, quick increase back down. So it's a lot less likely that you'll get thermal effects. The downside of this sort of facade is that it scatters light, and it scatters it over a really big area. So even though it's not particularly intense, you could still end up causing a nuisance. A flat facade impacts a much smaller area. And again, you aren't likely to have any issues with focusing. Geometrically, it's not possible. But you can run into thermal issues, because for any given point, the reflection is a lot more consistent, and you'll be in reflection a lot longer. So instead of a minute or two of light and then none, any given point that experiences a shadow could be in there for half an hour. And even with relatively low levels of extra irradiance, you could see some heating. And the last one is our concave facade. There's the big scary focal area. It creates at grade. Probably going to have some issues there depending on how reflective that glass is. But what's interesting is that once you get out of that focal area where those beams have diverged, it's really not any more intense than the convex case. And on top of that, it's affecting a much smaller area because so much of the light is focused right there. So that's probably the only saving grace of these kinds of facades, is that they tend to, if they are going to cause a problem, it's usually fairly close to the building. Now, for larger properties, that could be good because it's going to stay on your property. But as Tony Fenchard showed, in a tight, dense urban environment, that may not be close enough. If you're dead set on having a concave facade that faces a very sunny exposure, the next best thing you can do is sort of break up that facade. Don't have this monolithic kind of extruded curve all the way up. You can play with the radii of the different floors, use offsets, setbacks, create podiums, rotate the floors. Do anything really to break up that facade. What you accomplish by doing that is create multiple smaller focal points that are all going to be less intense. And these ones that are higher up will tend to occur in midair most of the time, which is really where we want these to be. If you can't affect the geometry of your building, the next best thing you can do is change the glass. So you can use frits, you can use anti-reflective coatings, tints. If you're feeling fancy, you can use these dynamic glazing systems, so ones that will change based on light levels, temperatures, or human control. On the horizon are these new kinds of coatings called retroreflective coatings. These act very similarly to low E coatings in the sense that they allow visible light through but reflect infrared. But they're designed at a nano scale to always reflect that light back up towards the sky. So it really cuts down on the amount of glare you're going to get at grade, which is pretty cool. As far as I know, these aren't commercially available yet, but it'll be very interesting once they are. Now, if you were paying attention, you may recall that I said none of this will work if the reflections are glancing, and that's true. These sorts of solutions will only work if you're seeing reflections that hit your building at less than glancing angles. For those kinds of reflections, really the only thing you can do is physically obstruct them. And you can do that using, brise soleils, if you're experiencing reflections from a lot of directions. If you're just concerned about the glancing ones, you can get away with just fins, vertical fins. And depending on how glancing those reflections are, they don't even need to be particularly long, or deep, I should say. Now, again, these come with their own consequences from a structural and aeroacoustic point of view, but that's unfortunately the way the game's played. If you can't change your building in any way, kind of your last ditch Plan Z sort of solution is to block any offending reflections at grade. And you can do that by building either artificial structures or by planting trees. Now, if you're blocking sort of focused reflections, you have to be very aware of how intense they're going to be to make sure that whatever you're putting in their way can tolerate that level of radiation. This is especially important with trees. There's unfortunately not a lot of research out there, maybe unsurprisingly, looking into the effects of these sudden intense increases in solar levels on plants. And one last thing I'll mention about the trees. It seems silly, but it happens. Make sure if you're going to use trees that they have leaves when you need them to. No, you're laughing, it's happened. If your reflections are occurring in winter and you're here in Toronto, a maple tree is not going to do you any good. It's just not. So on that note, I'll finish off this lecture. I'll thank Ted for putting this all together and giving me the opportunity to talk to all of you. Hopefully I've given you some food for thought working with buildings, and I'll open up the floor to the Q&A. Thanks.
That's always interested me, and that is, maybe I'll wait for the microphone. I guess the question I have to ask is, whenever we have people come here and do these things, one of the questions I ask is, well, if this became normative practice, so what do you think our capacity is in Canada to deal with if everybody that did any kind of design work did some kind of analysis like this? Mm-hmm. I mean, it'd be great for business, but how long would I have to wait to get an answer today based on how many people actually do this stuff?
Honestly, they're not that common now. So going forward, you would probably see an increase in the number of people doing it. You don't need necessarily any kind of specialized software to do a very quick sort of screening analysis. It's only when you find you have problems and need to kind of drill down to the specifics that you would need maybe more expertise. I recall seeing something online that right around the time 20 Fenchurch was announced, some kind of architecture nerd, for lack of a better word, took the publicly available model, threw it into 3D Studio Max or something like that, played with the lights, and then realized maybe it was something like a year or two before the problem was discovered that, hey, you're focusing a lot of light here. He couldn't say, you know, how much or if it would even occur given the climate in London, but he was able to identify the potential. So it's really, I mean, if you want to, you know, drill down to the details and maybe fix some of the more nuanced problems, you'll need a consultant. But this sort of stuff is easy to do with modern software. It really is.
And while this is going to whoever's going to ask the next question, just one last question. So where's the biggest hotspot and rough zone in Toronto, just so we all know to avoid it?
Toronto's actually not too bad for it. A lot of the buildings are flat. You don't see a lot of the curved ones here. And it's so dense that there's a lot of shadows too, so you get away with it. I can't really think of one off the top of my head here in the city.
Yeah. So actually, Professor Kesik was my thesis prof, so he'll know I'm here.
Oh, there you are.
So he'll know the research I'm referring to. So among the papers that I had researched, because I was doing a thesis on geometry and performance, and one of the parameters I used was light. So one of the papers actually was showing a facade that would incorporate PV cells in areas of the facade, and the geometry would try to focus the light into the PV cells. And now that, you know, I know that they're incorporating PV cells in glass, they're trying to incorporate them in materials that are standard in buildings, right? So I think it's an interesting question to see what the balance is between this kind of focusing the light and maximizing the production of the PV cells and controlling glare. So I guess it's not I don't know, is there any of your research, did you run into any of this type of problems?
I haven't seen anything using PV. There are test buildings that are designed to focus sunlight for heating purposes, or in one case, a solar oven. But yeah, building integrated PV would potentially go a long way, because you're going to absorb a lot of that radiation before it's reflected back from the building. You'd still have to watch for those glancing reflections again, but it would still be an improvement. And as for optimizing a building shape to feed those PV, that's absolutely something you could do. Just you're purposely creating one of these focal events to generate power. Yeah, that's absolutely doable.
You mentioned LEED certification. I was just wondering, in terms of the analysis that you were talking about, how much of that is required for LEED certification?
Really, just it's in terms of getting those daylight credits and view to sky credits for view out of a window. Those are kind of the main certification-based studies we do. As far as I know, nothing else that I presented has anything to do with LEED. The thermal comfort stuff does come up, like I said, with the Middle Eastern standards, because there's a lot more emphasis on maintaining that walkability through their really intense summers.
All right, everyone.